Recommendations for electronic circuits prototyping. Use a 30-watt soldering iron to solder your component in your board. Use a soldering iron and sponge with water to clean the tip of the soldering iron. Use a good quality soldering wire to wire up your prototypes. Use a proper wire wrapping wire to wire up your prototypes. Use soldering fume extractor to protect yourself from the fumes of the soldering wire. Use a good quality tin-coated wearer board for your prototyping. In previous session, we have studied that the minimum delay that can be produced by timer 0 of PIC16F877A is 0.2 microsecond. And the maximum delay that can be produced by timer 0 is 13.107 millisecond. In this session, we will learn that how these delay can be produced. From the datasheet of PIC16F87XA, we can see that the operating speed of this device is from DC to 20 MHz and the delay is that is 0.2 microsecond and 13.107 millisecond is calculated on the basis of 20 MHz crystal. With the help of this diagram, we can understand that how minimum delay can be achieved using timer 0. Here we have timer 0 register and the crystal oscillator is 20 MHz. After dividing the crystal oscillator by 4, we'll have a 5 MHz clock, and this clock will be applied directly to the timer 0. By setting PSA bit as 1, we can assign this 5 MHz clock directly to the timer 0. And here we can see if we'll assign the timer value that is 255, then after only one clock, TF0 interrupt flag will be set. So if we calculate the time of 5 MHz, it is equals to 0.2 microsecond. And if these bits, that is global interrupt enable, peripheral interrupt enable and timer 0 interrupt enable flag will be 1. So after 0.2 microsecond, the program counter of the microcontroller will go to the address that is 04 and will execute the interrupt service routine. Using this diagram, we can understand that how can we achieve the time that is 13.1072 millisecond. Here we have the crystal oscillator that is 20 MHz, and after division of crystal oscillator by 4, we'll have the clock speed that is 5 MHz. We can assign this 5 MHz clock to the timer 0 through prescaler by setting PSA bit as 0. And the combination of PS0, PS1 and PS2. Here we can find a table that the combination of these bits, if all 3 bits will be 0, the timer rate will be 1:2. It means that the clock speed will be divided by 2. Similarly, if we'll have all 3 bits as 1, so the clock will be divided by 256. And here we can find if we'll set all 3 bits, that is PS0, PS1 and PS2 as 1, so the clock that is 5 MHz will be divided by 256. And we'll have a frequency that is 19.53125 kHz. And this frequency will be applied through this switch to the timer 0. And if we load the timer with 0 value, then again this clock speed will be divided by 256 and we'll have a frequency of 76.294 Hz. And we can find the time of 76.294 Hz, which is equals to 13.102 millisecond. To get the interrupt, we have to set global interrupt enable, peripheral interrupt enable, and timer 0 interrupt enable. And if all these 3 bits will be 1 and if timer 0 flag will be 1, then the program counter of the microcontroller will go to the address that is 04, which is the interrupt vector for PIC16F877A microcontroller. With the help of this simulation, we can understand the operation of timer 0. Here we can find the timer register, which is of 8-bit, and the clock to the timer 0 is coming from prescaler. And here we can find the circuit of clock generation, and the frequency of clock is 512 Hz. And here we can see the prescaler selection bits, and here we can find 8 bits. Through these bits we can assign any value to the timer 0 with the help of this load input. And here we have interrupt service routine, and we have 3 inputs, that is global interrupt enable, peripheral interrupt enable and timer 0 interrupt enable. And here we have timer 0 interrupt flag. This flag will be 1 if all 8 bits of this timer will go from FF to 00 or 255 to 00. And this timer 0 interrupt flag is going to interrupt service routine. And here we have a routine if timer 0 interrupt flag will be 1 and if all 3 interlocking bits, that is global interrupt enable, peripheral interrupt enable and timer 0 interrupt enable bits will be 1, then the service routine will be executed and it will toggle the LED whenever the timer 0 interrupt flag will be 1. First, we'll understand the operation of prescaler. If all three bits are 0, then the clock division ratio is 1:2, and we are getting 256 Hz clock at the input of this timer 0. If I'll assign the value 1 to the prescaler, here we can see the clock is divided by 4 and we are getting 128 Hz. And if I'll assign the binary value 2 to this prescaler, then the clock division ratio will be 1:8. Here we can see the clock is divided by 8 and we are getting 64 Hz. Similarly, if I'll assign the value that is 3 to the prescaler, then the clock division ratio will be 1/16. Here we can see the clock is divided by 16 and we are getting 32 Hz. Similarly, we can assign the value from 0 to 7 to the prescaler. If I'll assign the value 7 to the prescaler, the clock division ratio will be 1:256. Here we can see the clock division ratio is 1:256. And here we can observe that timer increment speed is slow. If I'll assign value 0 to all three bits, in this case the timer 0 increment speed is higher, and the timer 0 is incrementing with a clock speed that is 256 Hz. Now we'll assign the value 1 to all three bits, that is global interrupt enable. Global interrupt enable is 1. Now peripheral interrupt enable is 1 and timer 0 interrupt enable is 1. And we can observe that whenever this timer 0 interrupt flag will be 1, this LED will be toggled through interrupt service routine, and the interrupt service routine will reload the value that is 000 to timer 0. Now we'll apply a low clock to the timer 0 using prescaler and we'll observe the operation of these preload bits. Here we can find the timer 0 is incrementing with a clock of 2 Hz. And now we'll assign the value that is FE to the preload bits. Here we have assigned the value that is F0 to the preload register. And here we have assigned the value that is FE to the preload register. And whenever the timer 0 interrupt flag will be 1, the timer 0 will be loaded with this value that is FE. Here we can observe. Here we can observe that on each interrupt, this value that is FE is loaded to the timer, and the interrupt service routine is executed after every 2 clocks. If I'll assign the value that is FF equals to 255 to the preload bits, and here we can observe that interrupt service routine is executed after only 1 clock. And if I'll assign the value that is F0 to the preload bits, here we can check F0 is loaded in timer 0. We have the similar arrangement in PIC16F877A. The clock speed in PIC16F877A is 10 MHz in our case, and we'll observe the same operation in PIC16F877A and we'll write a program to get the interrupt after every 1 millisecond. Here we can find the prototype circuit which we have wire wrapped in our previous sessions, and here we can find a 4-digit multiplex 7-segment display, and here we can see the circuit diagram for this multiplex 7-segment display. Here we have 4-digit multiplex 7-segment display, and this multiplex 7-segment display is common anode. Here we can see 4 control signals, that is AN0, AN1, AN2 and AN3 to control the anodes of these all 4 digits. If any control signal that is AN0, AN1, AN2 or AN3 will be low, then the 5 volts will be applied to the anode of the selected digit, and all 8 segments are connected to ULN2803 with the help of 100 ohm resistors. And ULN2803 is connected with port B of the microcontroller, that is from RB0 to RB7. And here we can see the 4 anode control signals, that is AN0, AN1, AN2 and AN3 are connected with RD0, RD1, RD2 and RD3. We will select the digit with the help of RD0, RD1, RD2 and RD3 and will apply the data through port B to display the numbers on these multiplex 7-segment displays. First, we'll write a program to execute an interrupt service routine to toggle this LED. Here we have a test LED, and this test LED is connected on pin number 18 of the microcontroller, which is RC3. We'll write an interrupt service routine to toggle this LED with a duration of 1 millisecond. We'll create a new project. OK, standard project. and the project name is T0ISR project, and the project folder will be in microC projects. We'll create a new folder and we'll assign the name to this folder, that is SSD projects, 7-segment display projects. OK, and the microcontroller is PIC16F877A. The clock speed is 10 MHz in our case. OK, next. Finish. And here we have our main program starting from void main. First we'll write some comments and assignments to our project. Here we have assigned the name to our project, that is timer 0 interrupt routine. Now we'll write bit assignments. We will write define test LED port C.F3. As we know that the test LED is connected to port RC3. So here we have assigned the name to port RC3, that is test LED. And now we'll write our main program. And here we have our main program starting from void main. So first we'll assign the direction to the ports, that is trace B equals to 0. It means that port B is configured as output port. Trace D equals to 0. It means that port D is configured as output port. Here we can add comments. Now we'll configure port C3 as output port, that is trace C.F3 equals to 0. Port RC3 is configured as output port. Now we'll initialize port B, port C and port C3, that is port B equals to 0. We have assigned the value 0 to port B. Port D equals to 255. We have assigned the value, that is 255, to port D. It means that all 8 bits of port D will be high. In this case, no 7-segment display is selected. Here we can see the lower nibble of port D, that is RD0, RD1, RD2 and RD3. All these pins are connected with the controls of anode. And we can find the higher nibble of port D, that is RD4, RD5, RD6 and RD7. All these 4 bits are connected with the switches. So we have assigned the value, that is 255, to the port D. Now we'll assign the value 0 to port RC3. Here we have initialized port RC3, and now we'll assign the value to timer 0, that is TMR0 equals to. Now what will be the value of timer 0 register to get the interrupt of 1 millisecond? In our prototype, the crystal value is 10 MHz. After dividing the clock, that is 10 MHz by 4, we will have a clock speed, that is 2.5 MHz. And if we'll assign the value, that is 101, to prescaler, here we can see from this table that if we'll assign the value, that is 101, so the timer rate will be 1:64. So if we'll divide the clock, that is 2.5 MHz by 64, so we'll have a clock speed, that is 39.0625 kHz. Now with the help of this equation, we can calculate the value of the register to get the interrupt after every 1 millisecond. So we'll place the value in this formula and we'll get the value. The required time is 1 millisecond. The clock speed is 10 MHz and prescaler rate is 1:64 multiplied by 4. So we'll get the value, that is 216.9375, which is approximately equals to 217. So we'll load the value that is 217 in timer 0 register. So if we load the value that is 217 to the timer register, so after 39 steps, timer 0 will reach to 255 and timer 0 interrupt flag will be 1. And if all these 3 bits, that is global interrupt enable, peripheral interrupt enable and timer 0 interrupt enable will be 1, then program will jump to the interrupt service routine. So if we'll divide the clock speed that is 39.0625 kHz by 39, we'll get a clock speed that is 1001.6 kHz. And the time duration for 1001.6 kHz is equal to 0.9984 millisecond, which is approximately equals to 1 millisecond. So we'll load the value that is 217 to the timer 0.